Hello there, welcome to this video. This is the second video in the unit circle, and what I'm going to talk about today in this video is how do we get the coordinates for our unit circle. So in calculus, a lot of times we're going to be asked what is sine of this angle, what is cosine of this angle. Well, we need to go ahead and we need to know coordinates or locations on the unit circle. So that's the purpose of this video. So let's go ahead, let's look at our unit circle, and here it is. I've kind of taken out all of the angles that we've had, and I really just want to focus on coordinate locations of this unit circle. And kind of what I'm going to go ahead and do is similar to what I've done in the past video. Is I'm going to start out with my quadrantals. So, and I want to focus on if you will, this distance here. So how far is it to this point? Like, what's its coordinate location? Well, if you consider the center of the unit circle as an origin, 0, 0, well, this distance, right, is your x value, and we know that the radius of a unit circle is 1. So the height would be 0. So that coordinate location is 1, 0. And these quadrantals are very easy, right? I'm back at the origin, right? This is 0, 0, if you will. Okay, and I go up, okay, so 0, 1, right? I didn't go anywhere left or right on the x-axis. Now I can go ahead and I can go back from the origin and go to the left one. Well, that's -1, and I didn't go up at all, so that's 0. Okay, how about to the bottom? Well, again, left, right, I didn't move at all, so that's 0. And then I went down 1, so that is a -1 distance. Okay, so those are the quadrantal coordinate locations for 0, right? 0 and 2 pi, and then up here, pi halves, over here, pi, and then down here, 3 pi over 2. Okay, next, let's go ahead and let's talk about our pi 6 angles, or our 30-degree angles. So we know that this location, right, is 30 degrees, okay? And if this is a right triangle that is made, then I know that this angle is 60 degrees. Okay, which brings us to our next topic of kind of how these points are generated is special right triangles. So I'm going to introduce you into well, I guess it's 3 special right triangles. Really, it's only 2 because 2 of them are the same. But we have 2 special kind of right triangles. We have a 30, 60, 90 triangle, okay, and those are exhibited here and here. And we also have a 45, 45, 90 triangle, which is exhibited here. Okay, so these are special right triangles because they have a pattern that holds with the Pythagorean theorem, and that's how we find their sides. So the pattern for a 30, 60, 90 triangle is that their side lengths are 1, √3, and 2, right, corresponding to your biggest angles. So the biggest angle has 2, smallest angle has 1, and then the 60-degree angle forms √3. Okay, and I can go ahead, if you wanted to verify this with Pythagorean theorem, you could. A squared plus b squared equals c squared. Be my guest. You can go ahead and do that. I mean, or you can take my word for it, right? Those are special right triangles, and those kind of relationships between the side lengths always hold. What I do want to talk about before we dig into the 45, 45, 90 is what is sine and cosine of these values. So we know that sine of 30, if this is my 30-degree angle here, sine is opposite over hypotenuse, so that is 1/2. And cosine is adjacent over hypotenuse, so √3 over 2. Okay? So I hope those kind of stick in your head. We'll come back to those. And then sine of 60, so I'll play the same game here. If this is my angle, I want sine of 60, okay, opposite over hypotenuse, √3 over 2, we know Schwarberg. Okay, cosine adjacent over hypotenuse, we know Schwarberg. Okay, and I hope you kind of see some similarities here between these 2 triangles, because those values kind of just flip-flop, right? And again, like I said, we'll come back to this. Okay, 45, 45, 90. The relationship for a 45, 45, 90 triangle, since it's an isosceles triangle, right, is 1, 1, and then Pythagorean theorem gives you √2. So 1, 1, √2. So if I want sine, that's opposite over hypotenuse, that gives me 1 over √2. Well, we know that we can't have a radical in the denominator, so we rationalize, so we get √2 over 2, and that is sine of 45 degrees. And I can play the same game, right? I get 1 over √2, which if I rationalize gives us √2 over 2. Okay, so those are sine and cosine of those angles. Okay, so what, Schwarberg? Why did you talk to me about special right triangles? Well, I'm so glad you asked, because back here in our triangle, I have one of those special right triangles. This is a 30-degree angle, and if it comes straight down, I get a right triangle, making this angle 60, okay? So I know that this side is 1. I know that this distance is 2, and I know that this distance is root 3, okay? Except there's one problem. We're in a unit circle, and I know that the radius of a unit circle is what? 1. So, okay, what can I do to make 2 1? I'm just gonna go ahead and reduce. I'm gonna divide everything by 2. So 2 over 2, okay? I'll divide this by 2, and I'll divide this by 2. So now if I go ahead and reduce 2 over 2, which we know is 1, okay, I get this triangle, and the values still hold, right? So I have now, if I want the coordinate location of this point, okay, well, I need an x and a y. Okay, so what's this distance to get here? Well, I travel along this distance to here. Okay, well, didn't I just travel root 3 over 2, that side of that triangle? Okay, so that's root 3 over 2. Okay, what about the y value if I go up? Well, I have to go up this distance to get there, and that is 1/2. Okay, so hey, what you just did is you found the coordinate locations, right, for pi over 6. That's what you just did using that formula, right? So, or not formula, for those calculations of the triangle. So those are the coordinate locations for pi over 6. Now, what I want to talk about is all of the other pi over 6 angles, because if we go back to our unit circle, which we made in the last one, you'll notice that I have a pi over 6 angle here, a pi over 6 angle here, and a pi over 6 angle here. They all have a denominator of pi over 6. Is there any connection? Oh yes, there is. They are what is called reference angles. So here's a reference angle, and it's called theta prime. Of an angle theta in standard position is the acute angle formed by the x-axis and the terminal side of theta. That's very, very important. That's what a reference angle is, formed with the x-axis and the terminal side of theta. So here's kind of an example. If I want to go ahead and I go back to my unit circle here, and I want to draw an angle. Okay, and I go around and I want to end here. Okay, this is 5 pi over 6. Well, but what I also have is I also have this angle here, which is pi over 6, and it's a reference angle. So what I get is I get another 30, 60, 90 triangle right here. Okay, and what's big whoop? What's the purpose of it? Well, those distances hold. If I all of a sudden go this direction, okay, my value is negative root 3 over 2, right? I went to the left, so it's negative. And I went up this distance, which was 1/2, right? It's the same exact as this triangle over here to get that coordinate point. Oh, so what you're telling me is that all of the reference angles, coordinate locations are the same? That's exactly what I'm telling you, right? So here is another reference angle, 30-degree reference angle, or a pi 6 reference angle here, right? Here's 30 degrees. Okay, so this distance, if my x value, if I go this way, it is negative root 3 over 2. Okay, and I have to go down that distance, that y value distance, which is negative 1/2. And I hope what you're picking up on is the pattern, right? I hope you see another 30-degree reference triangle here. Okay, so this value is positive root 3 over 2, comma, negative 1/2. Okay, and that's that coordinate location. All right, so those are the 30-degree angles. Wow, so there's more? Yeah, we also have our 60-degree triangle, which is here. Okay, and if I go ahead and do this, so now this is 60 degrees. This happens to be 30 degrees. So what I want you to see or envision is it's the same exact triangle, right? Same exact triangle. Right? This is the 31, here's the 61. The side lengths are exactly the same. They just switch, right? So all of a sudden now, okay, this horizontal distance is 1/2. This distance is √3/2, and my hypotenuse is 1. Okay, so that means my x value is 1/2. That means my y value is √3/2. Okay, and I have those coordinate locations. Okay, and this pattern holds. So I can go ahead, I can go up here. So this is 1/2, -1/2, √3/2. Okay, this pi6 or pi3 angle down here is going to be -1/2, -√3/2. Okay, and this one down here is +1/2, -√3/2. Okay, and again, I can go ahead and I can put those in because they're all reference angles, right? I have a 60-degree angle. I'm making that value, okay, in those quadrants. I have a triangle formed with the x-axis. So all those values hold, okay? And that's kind of the cool thing. So when we look at our unit circle, okay, and I have, and I'm asked something about a 5π/3 angle, well, I know it's going to match exactly the same as π/3. All right? Okay. We just have one left, okay, and that is our 45-degree angle. So let me go ahead and erase. And I apologize, I switched up my colors. I used blue for that pi3 angle. I hope you're not too caught off guard. Okay, so I'm going to go ahead and draw a triangle here. And I know that this is a 45-degree angle, right? So this side is 1, this side is 1, this is √2. And if all of a sudden I divide everything by √2, okay, what I get is √2/2. Okay, so here √2/2. So this distance now is 1, okay, and my x distance is √2/2, and my y distance is √2/2. Okay, not too complicated. And then also too, I can go ahead and replicate this again in every other quadrant. So here I have another, okay, reference triangle. So -√2/2, and this is +√2/2. Okay, I can go to quadrant 3 to this angle here. So it is -√2/2, and this is √2/2. And in my fourth quadrant, okay, x is positive, so √2/2, and my y value is negative, √2/2. Okay, so all of these values, they're the same in every single quadrant, okay, except you have to think about your positives and negatives, right? So here in quadrant 1, okay, I know that the x values are positive and the y values, right, are positive. In quadrant 2, okay, your x values are negative and your y values are positive. In quadrant 3, okay, x's are negative and y values are negative. And in quadrant 4, okay, you have positive x values and negative y values. Okay, all right, so there's one last thing that I want to go ahead and talk about, is the connection to the trigonometric values. So each of these values actually represent a particular trigonometric value of that angle. So I want you to kind of pick up on, so here is these values. This is for a 30-degree angle. Okay, I get these values. This is my x value and my y value. √3/2 and 1/2. Okay, and I'm going to go back to my special triangles here, and I want you to look at the 30 degrees. What do you notice about these values? Hey, aren't these the same coordinates, right? Wasn't this my x value, my √3/2, and wasn't this my y value? So if I go back to my triangle, right, you can see that this value, your x value, is cosine of 30 degrees. And the y value is sine of 30 degrees, right? They match, It's the same exact value, right? That's sine of 30. Okay, so I want you to go ahead and now see that that pattern holds for every other angle. Let's go ahead. Notice how those values switch for sine, right? So your x value is 1/2, y value root 3 over 2, and indeed it is true up there, right? And if I go ahead and go back to my 45-degree angle, okay, again, this is your x value, this is your y value. I know they're the same, but it's root 2 over 2, right? So we come up with this idea that our x value is cosine theta and that y is sine theta. Okay, very, very important. Put a box next to that. All right, and that is it for introducing the coordinates of the unit circle. All right. I will catch you in the next video. We'll go ahead and talk about how do I find trig calculations of angles of the unit circle. Catch you next time. Peace out.